This chalkboard represents a common hurdle in science education, a wall of formulas, like the chemical makeup of hydroaluminum silica, presented without any physical context. For many students, these are just abstract characters to be memorized for a test. But in the Special Region of Yogyakarta, Indonesia, a different pedagogical approach is taking root. Educators here are moving the lesson out of the classroom and into the workshops of local artisans. This is the Ethno-STEM paradigm. It's a method that uses local indigenous traditions as the primary setting for teaching science, technology, engineering, and mathematics. We can see this in the Kasongan Pottery Project. In this program, students are challenged to master modern scientific concepts by physically producing traditional clay pots. By treating these cultural artifacts as primary research subjects, students begin to identify the specific engineering, physics, and mathematical principles required to make them. The engineering begins with material processing. Students must refine raw hydroaluminous silica clay through filtering and precise moisture management. This microscopic view shows why moisture is vital. Clay particles are separated by a double diffusion layer of water molecules that prevents them from touching. If dried too rapidly, this layer collapses. Particles crash together, causing sudden, localized shrinkage that cracks the entire structure. Traditional Kasongan artisans solved this through a slow drying process. By allowing water to evaporate gradually in a controlled environment, the clay particles settle into a stable, uniform arrangement. These preparation techniques are practical applications of structural engineering, developed to prevent material failure at the molecular level. Once stable, the clay is moved to the turntable. Here, the artisan's hands guide the wet clay as it spins, manually executing the bowl's form. The mortar's shape follows a mathematical rule. Its slope is a parabolic curve from slicing a cone. Cylindrical items require maintaining a constant radius along the vertical axis. Complex jars demand reflectional symmetry, ensuring both sides are mathematically balanced to prevent collapse. The potter's wheel acts as a laboratory for applied geometry, where the physical outcome is entirely dependent on mathematical precision. The process concludes with the biscuit firing. Here, fragile clay pieces are stacked into an open-air furnace and exposed to direct flames. This requires precise thermal management. The fire must reach between 700 and 1000 degrees Celsius, depending on the specific hardness of the clay. At these temperatures, a chemical reaction occurs. Heat energy permanently strips away absorbed water molecules from the clay's molecular matrix. With the water gone, the clay undergoes a phase shift. The soft paste permanently transforms into a dense, rigid, and waterproof ceramic lattice. The firing process uses thermal energy to trigger a permanent chemical change, turning a brittle shape into a durable solid. The final phase of the project takes students from the workshop to the Market Day Bazaar, where they test their products in the local economy. Success requires a different kind of calculation. Students weigh raw material costs and physical labor against final pricing, finding a price point that is competitive enough to sell, yet yields a profit. These finished ceramic pieces are the result of that entire process, from molecular engineering and geometry to thermodynamic firing and market analysis. Ethno-STEM projects demonstrate that traditional crafts are deeply connected to formal scientific inquiry. By working through the technical logic of these traditions, students learn to use community heritage as a practical foundation for entrepreneurship and local industry.